In this video, we're going to be solving Leetcode question 162, which is find peak element. Let's get started. So in this question, we are given an array of numbers, and all we need to do is return the index of any number that is a peak element. And a peak element is defined by a number which is greater than the number next to it on the left side and on the right side. So in this array, as an example, the number 3 would be considered a peak element because the number 1 is to the left of 3 and 3 is greater than 1, and 2 is to the right of 3, 3 is also greater than 2. Because it's greater than both its left neighbor and its right neighbor, it is considered a peak element. And again, our goal is to return one indice for any one of the peak elements within an array. One important note is that a number on the end of the array is also considered a peak element if it is bigger than its only neighbor. So what they say in the example is to imagine that there was another element which is negative infinity. So then 5 would be a peak element as well because it's bigger than 1 and everything is bigger than negative infinity. So in this array, 5 is a peak element, 3 is a peak element, and 6 is a peak element. Those are the 3 that we could possibly return. All right, as always, we're going to start with a brute force solution. And in this case, we can come up with a fairly simple brute force solution by just checking every single element in the array from left to right and seeing whether that element is a peak element or not. So for the first element in the array, we would just check if it is bigger than its neighbor on the right, and it is. So technically we would end it here. But assuming that wasn't a peak element, we would then go to the next element and then check if it's larger than its predecessor or larger than its the next element in the array. And then we keep doing this scan over from left to right, checking each individual element until we find one, let's just say here, which is bigger than both of its neighbors. And then we would be done. So this solution would take O of n time, where n is the number of elements in the array. And that's because we're checking every single one. At worst case, it's going to be like a strictly increasing array. So the last element is the only peak element, and we're going to have to look through every single one to verify that. The solution is O of 1 space complexity, though. We don't need any extra space to do this solution. Okay, so that solution is okay, but we can definitely improve it by getting rid of some unnecessary computation. And there is an important insight that could be very useful for solving this question. Again, remember that we only need to find one peak element in the array. Not the first peak element, not all the peak elements, just any peak element in the array. So let's say we just take a look at the number 2 right here. And then we want to check whether that is a peak element or not. So we compare it to the element to the right of it, and it is greater, so that's good. But it's not greater than the element to the left of it. So unfortunately, 2 is not a peak element, so we need to keep looking. But if we were to decide whether we want to look to the right of 2 or to the left of 2, which should we choose? Well, the answer is we want to look to the left of 2. And the reason being is the left neighbor to 2 is larger than 2. So now let's take a look at 3's perspective. We already know that 2 is smaller than 3. So that means 3 is bigger than 2. So no matter what, one of the neighbors to 3 is already bigger than 3. Now, if we check the other neighbor to 3, if it is smaller, then 3 is a peak number. So that's good. But if it happens to be bigger, let's say this was a number 5, well then 3 wouldn't be a peak element, but then 5 is in the running to be a peak element because we already know it has one neighbor that's smaller than it, so it just needs one more. And it turns out that if we just look at this side of the array, and we chose this side because 3 is larger than 2, there must be a peak element in this subsection of the array. It's either going to be an intermediate element, so like 5, for instance, because it's bigger than 3 or 4. It's also possible that the numbers are strictly increasing order. So let's say it's like 3, then 4, then 5, then 6. And this would also yield a peak element because you just go all the way to the end of the array. And 6 is a peak element because it's bigger than 5 and there's no element to the left of it. So it is a peak element. So whenever we look at a number, if we find a neighbor that is greater than it, then we know we can find at least one peak element in that side of the array. So again, going back to that initial example, if we check 2 and we find that 3 is greater than 2, then something on the left-hand side of 2 is going to be a peak element. The strategy I just mentioned should ring a bell because it is very similar to the binary search algorithm. As a refresher, the binary search algorithm is a specific search algorithm that can only be used when we have a sorted array. So for example, our array is these numbers from 1 through 7, and we need to find the target element of 3. In binary search, what we would do is first check the middle element. If the middle element is equal to the target, then we're done. If it's smaller, then we're going to cut out this entire section of the array because we know the target, if it exists, is going to be on this side of the array. And similarly, if the target was larger, we would cut out this entire section of the array and then only search this remaining piece because we know for sure that if a target exists, it's going to be on this side of the array. And this is why binary search is so efficient, because every time we do a comparison, we cut the solution space in half. So therefore, a binary search algorithm is going to be log n, time complexity. In the case for this specific problem, we can apply a very similar algorithm to binary search. First, we're going to check the middle element. And whenever we check an element, one of 3 things can happen. Either it is bigger than both its left neighbor and its right neighbor, in which case the element itself is a peak element. So we could stop right there. We already found a peak element, which is 3. Another thing that can happen is the element is bigger than one of its neighbors, so 3 is bigger than 2, but it's smaller than the other neighbor. So now we can cut the search space in half because we know there's going to be at least one peak element on the side of the side that contains the larger neighbor. So in this case, the larger neighbor is 4, so we can check this side of the array, and we're guaranteed to find a peak element somewhere in here. And the last possibility is that the middle element is smaller than both the left neighbor and the right neighbor. And in this case, we know there's going to be a peak element on both the left side and the right side. So it doesn't really matter which we pick. Since we're only looking for one, we can choose either. So let's just choose the right-hand side always for simplicity. So no matter what happens, we're going to either find a peak element or we're going to narrow down the search space in half. So therefore, our algorithm is going to be as efficient as binary search, and it's going to take log n time complexity. And it's still constant space algorithm. So now that we have the algorithm all written out, let's code it up. If you're finding these videos helpful, I think you'll love what we got going on in our private community. We dive even deeper with exclusive content that won't be shared on the main YouTube channel. I also offer individualized coding interview study plans that are tailored just for you. You can also join small group sessions, participate in mock interviews, and get your questions answered in live weekly Q&As. It's a great way to take your coding interview prep to the next level. If you're interested, check the link in the description below. I'll see you inside. All right, so here is the Python code for solving the find peak elements question. I wrote out the general algorithm above. It's going to be very similar to binary search as I explained earlier. We're going to first start by checking the middle value. If the middle value is a peak value, we're just going to return the middle value's index. If it's bigger than one element, smaller than the other, we're going to reduce the search space to the side of the array that contains the bigger neighbor. And if the middle value is smaller than both of the neighbors, then we're just going to, either one will contain a middle element. So I think here I just said, yeah, we're going to take the left-hand side always, but we can take the right-hand side too. It doesn't really matter. So first we're going to set up our base cases. They're never going to give us a array with length 0. So the first possible case is an array of length 1. And since there's only one element, that itself is going to be a peak element. So we just return 0, which is that element's index. If the array has a length of 2, then there's going to be one element that is larger than the other elements. So we just check which one that is and then return the appropriate index. Otherwise, so if the array is greater than 2 in length, we're first going to find the mid index. We're going to check if the mid index is a peak value. And if it is, we're just going to return that mid index. If the mid index is smaller than one of its neighbors and greater than another one of its neighbors, both of these cases are going to test for that. we're just going to do this recursively. You could do this recursively or iteratively, but I recursively basically took out half of the array and then put this back into the same function, the find peak element function. So in this case, the left neighbor is going to be bigger, so that's why we take the left-hand side of the array. And in this other case, the right neighbor is going to be bigger, so we take the right-hand side of the array. And whenever you take the right-hand side, don't forget to update the index, because if you basically you have to add on all the elements that you took out. So it would be mid plus 1 here. And then otherwise, so this is the case when both neighbors are larger than the mid element. We're just going to take the left-hand side for simplicity. So this is functionally, it's going to look exactly the same as this case. Now let's run the code. It passes the test cases, and then we'll submit. And it does well in both the runtime and the memory. So that's that.